My guest today is Tom Shula.
Thank you very much for having me. I am a semi-retired physicist, live in California. My training was in theoretical physics, entered a PhD program, and quite frankly, what happened to me was I became somewhat disillusioned with the environment there and decided to leave with a master's degree and work in tech industry. Most of my work was in the area of semiconductor and disk drive component and system development and manufacturing. I had a few diversions into some other industries, and so I had the opportunity to work in places like steel mills, refineries, food processing centers, waste treatment plants, and things like that. In my work, I've dealt with a lot of different kinds of fluid dynamic systems with pressures ranging from thousands of pounds per square inch down to 10 to the minus 12 Torr, which is getting close to outer space, and temperatures anywhere from liquid nitrogen up to over 1,000 degrees centigrade. I've always been an extremely curious person, even at a very young age. Sometimes I tell people I feel like I've been a scientist all my life. And in my professional and technical career, I was considered to be a top problem solver, and I did a lot of work in failure analysis and developing advanced manufacturing technologies and things like that. I've been following the climate change issue ever since the global cooling scare of the 70s. I was a much younger man then, but found a lot of interest in it. And I think basically I'll just segue from that into talking about what my approach has been for my presentation here. As I follow the climate change debate, the focus on the climate realist side, from my perspective, has been to debate a lot of the details of what actual versus modeled results in the future might be. And I think that's important. And I respect all of that work. And quite frankly, it's been very helpful for me to understand what some of the fundamental issues are. But I've always been kind of a root cause guy. I've always believed, based on my professional experience, that the fundamental assumptions behind the greenhouse effect were incorrect. So my focus has been to find experimental proof that the greenhouse effect is a false concept. And after many hours, many years of, accumulating information and giving it a lot of thought and looking for, various alternative perspectives, I had an insight several months ago, and that's what I'll be presenting today. So what I've called this is a novel perspective on the greenhouse effect. And as a subtitle, it's what a heat loss vacuum gauge can teach us about energy balance in the lower atmosphere. With this diagram, NASA publishes these from time to time. I'm not sure this is the most current one, but this is their model of energy balance in the atmosphere, where the yellow arrows indicate incoming solar radiation energy, and the red arrows indicate the outgoing long wave energy, infrared coming from the Earth, going back out into space. This one is an example. The values, they change from time to time. That's part of their parameterization of the climate models. And one of the things to keep in mind about this model, it's limited because it's static. It basically is assuming a flat one-sided Earth without any diurnal day and night variation, which makes the world actually a much, much more complex dynamic system. And because of that, the energy flux numbers in the diagram are 1/4 the actual peak value of the solar energy flux. The thing we'll be focusing on here is what's happening that is cooling the surface of the Earth. And so if you look at the NASA diagram, ultimately on the left, they say that there are 163 watts per square meter being absorbed by the Earth's surface. And then next to that, you say emitted by the surface are 398.2 watts per square meter. And, one might wonder right away, how do you have 163 going in and 398 going out? And this is where it starts getting a little complicated, and this is where the greenhouse effect comes into play. Then you see next to that, there's also something called back radiation, which is 340 watts per square meter, which is, purportedly infrared radiation that is being re-emitted by the atmosphere and coming back to Earth. And the concept behind the greenhouse effect is that this going back and forth of radiation is what keeps the Earth from cooling down too fast. And that's kind of a simple way of putting it. And this is what I believe is the fundamental problem in the modeling of the atmosphere as we know it. And then I'll also mention off to the right, there's a small contribution of outgoing energy from thermals, convection and conduction. And then we have latent heat, which is basically evaporation, condensation, those processes, which latent heat isn't actually a transport mechanism, but it is a form of energy. Let me go on to the next slide, and then we'll talk about how the Earth actually loses its energy. So we know in physics there are three mechanisms that are available to transport heat. We have radiation, we have conduction, we have convection. Radiation is basically the way heat energy can be transported through empty space in a vacuum. And in order for heat to be transported by radiation, the radiation has to come from something, and then it has to land on something, and then that radiation interacts with the atoms of the receiving body, and the atoms get excited, and that manifests itself as heat. Conduction is when two materials are in contact with each other, or if you take a steel rod and you heat one end, the heat will move down the rod and eventually the other end will become warm. And then convection is the form of heat transport, probably most easily illustrated by boiling water in a pot on your stove, where the water on the bottom of the pot gets hot, its density decreases, it rises, and it creates a current of circulation that eventually mixes the water so that it all gets hot. And the same thing happens in the atmosphere. And then in the model, if we go back, there are three components of heat transport upward from the surface. And this is a detail I want to make clear. If we look at the red arrows, we have the heat that's emitted by the surface. We have the convection, the small one at 18.4, and then we have the latent heat. So the argument behind the greenhouse effect is that radiation is the primary driver of transporting heat from the surface of the Earth to the atmosphere. And that's illustrated very clearly here because we have almost 400 watts per square meter coming from the surface, and we do have this component of back radiation, but that back radiation is necessary in order to make the model agree with what we observe. So let me go back to the slide. Okay. So the radiation component, as I just said, indicated by the long red arrow, is 398.2 watts per square meter. There's a convection component at 18 watts per square meter, and then the latent heat at 86. So, I said, well, where do we get that value of 398 watts per square centimeter if there's only 163 coming in? Well, that comes from taking the average surface temperature of the Earth, treating the Earth as a black body using the Stefan-Boltzmann law. And based on that, you can determine the power output. And it turns out it's 398 watts per square meter. I'm not sure where NASA gets their values for conduction, convection, and latent heat. Based on all the investigations I've done and what I can find out about how they create these models is that they estimate these numbers to make things balance the way they like for them to turn out. And then the back radiation component is based on treating the atmosphere as a black body, and that the atmosphere is radiating downward to the surface. And when I get to the end of the talk in the appendix, we'll talk about black bodies and Stefan-Boltzmann law. But For purposes of my approach, I'm only considering the upwelling radiation from the surface. And again, this is NASA's claim that 398 watts per square meter of radiation is coming up from the surface, and that the conduction convection component is only 18.4 watts per square meter. And it doesn't mean that the latent heat component is not important. It's very important. Water vapor is a major player in heat transport in the atmosphere. But for purposes of understanding how the greenhouse effect supposedly works, all I want to do here is compare the radiation component claimed by NASA to the convection component claimed by NASA. And according to that model, if we use the numbers 398.2 and 18.4, and we take the sum of those two, the radiation component, according to NASA, is 95.5%, and the conduction convection component is 4.5%. Once I came up with all of those numbers, it became apparent what we need to do is we need to figure out whether or not those numbers represent reality in any way. In the climate models, radiation is assumed to be the primary mechanism of heat transport. But we want to measure the actual relative contributions of conduction and convection versus radiation. And it just so happens that there is an instrument that was designed to do that over 100 years ago. It's been around for a very, very long time. And that instrument is called the Pirani gauge. So this is a picture of the Pirani gauge. I'm familiar with this because I had a lot of experience in the vacuum industry processing components for semiconductors and disk drives and things like that, where you're typically operating under very high vacuum conditions, but you need to be able to monitor the vacuum both, in the transition from atmospheric pressure down and then, continuously while you're operating. And the Pirani gauge is a very interesting device. And the next slide, I think, is going to be kind of busy. I didn't bullet point this one so much because I couldn't figure out how to bullet point it. But it was invented in 1906 by Marcello Pirani. He was a German physicist working in a light bulb factory, and they needed a way to reliably measure the vacuum when they were making incandescent light bulbs, which actually have fairly stringent vacuum requirements so that the filaments don't oxidize and burn out. In the Pirani gauge, if we go back, you can see there's a sensor wire that runs through the center of the gauge, and that wire is heated to maintain a constant temperature. They use something called a Wheatstone bridge. You might be familiar with that since you're a double E. There are four ways that energy can be dissipated from the filament. We have conduction, which would be when the air molecules impinge on the filament and take heat away from it. There is convection, which is movement of the warmer air molecules away from the filament, and then the cooler ones come in. There's radiation. And then there's also something called end losses, which is because you can't totally isolate that filament. There's a certain amount of heat that will leak out through the device itself. But the basic principle behind the gauge is that if you take all of the air away so that there is no conduction and convection, the only way that the filament will lose heat at that point is by radiation. Once you introduce gas into the instrument, the gas starts having collisions with the filament, and it will take energy away from the filament. And so the current, or you could say actually what they monitor is the power into the filament has to increase in order to maintain the temperature. And that's basically the principle behind it. So as more gas enters the gauge body, one has to increase the power into the filament in order to maintain the filament temperature. So the filament continues to radiate the same amount of heat, irrespective of the temperature. But what happens is we can measure by the amount of power going into the filament how much power is being absorbed by the gas versus how much power is being lost to radiation. So if we look at the red line on this chart, the one that's called combined radiative and end losses, that basically just says that irrespective of the pressure, we're maintaining the temperature of the filament at a constant value so that the radiative losses and the other leakage end losses are constant. But if we look at the chart, what we see is that those radiative and end losses are approximately 0.4 of a milliwatt. And looking at the curve, you can look at either the blue curve for the gas loss or the green curve for the total loss. If we go to the right side of the chart, the very end of it would be 1,000 torr. 760 torr is atmospheric pressure. And it's pretty easy to interpolate there. At 760 torr, it requires about 100 milliwatts to maintain the temperature of the filament. So what that's telling us is that the radiation is accounting for 0.4 milliwatts of that power, but the loss to the gas is 99.6 milliwatts. So the gases are actually taking away 99.6% of the power that goes into the filament. Now, I made a little chart that one can interpolate from the graph. So at sea level, at 760 torr, the radiation contribution is 0.4%, and the conduction and convection contribution is 99.6%. At 10 torr, which is a factor of almost 100 less, it's actually at 110,000 feet, we would not be able to survive there, but there's still adequate convection that the radiation component is only 0.7%, and the conduction the contribution due to conduction and convection is 99.3%. And just as a final example, if you look at the crossover point where radiation and convection-conduction balance at about 50-50, that's at about 20 millitorr, which would be equivalent to close to 250,000 feet, if you want to think of it that way. On the other hand, if we look at what the greenhouse effect model says, it says that the radiation contribution is over 95%, and the conduction-convection contribution is less than 4.5%. So, my question is, which of these is more likely to affect, to represent reality? And I think experimentally, the Pirani gauge basically tells us that at, pressures near atmospheric pressure, the heat loss from the conduction and convection is overwhelming relative to the radiation component. There may be individuals that, will disagree with this, but, the filament in the Pirani gauge is analogous in this experiment to the surface of the Earth. And I'll mention, it's not, these filaments are not, glowing red hot or anything like that. The temperatures typically are between 50 C and 100 C. In order for the gauge to function, it just needs to be above room temperature. And the temperature is typically chosen to manage where the saturation occurs and what the slope of the curve is based on the range of pressures that you want to measure. But as the pressure rises, more air molecules collide with the heated filament, which gives the molecules more energy, which then with more energy, they tend to rise. Cooler molecules come in. You have conduction, convection, and it's perfectly demonstrated by the operation of this gauge. And there are many other embodiments of this device people have made. There's one reference in my paper to a group of scientists who made a thin film version of the Pirani gauge for small spaces, and it actually has a planar filament, if you will. It's a small heated square that operates with the role of the filament in the Pirani gauge. I'll just say that at the surface of the Earth has a tremendous heat capacity relative to air. And we'll talk about air a little bit later to put some of this in perspective. But what's basically happening is that the number of molecular collisions occurring at atmospheric pressure, they're so efficient via conduction and convection at removing heat from the surface that they basically overwhelm any potential contribution from radiation. Some of these other embodiments of the Pirani gauge actually have the radiation component down as low as 0.1%. So as the pressure rises, as I said, we create conduction and convection. It's demonstrated by the Pirani gauge, and I can only speculate, why no one has looked at this in the past, but that's the case. So from the standpoint of the experimental evidence, my conclusions, that I would present are, the Pirani gauge provides a method to measure the relative contributions of radiation versus conduction and convection in a gaseous environment. And the performance of the Pirani gauge indicates that at pressures relevant to the lower atmosphere, radiation accounts for less than 1% of heat transport. So let's say the greenhouse effect, if it exists, is based on radiative heat transport in the lower atmosphere. And so if it does exist, it plays an insignificant role in heat transport in the lower atmosphere because it's less than 1%. The climate models are generally based on radiative transport. And because the Pirani gauge demonstrates that this can't be the case, then that's a false assumption in these models, and we really can't consider them to be valid. And then finally, because these models are based on the greenhouse effect and that supposedly implies anthropogenic global warming, I would argue that there is no scientific evidence for anthropogenic global warming. That, radiation is a minor player in the Earth's atmosphere as far as heat transport is concerned. The alternative explanation for why the temperature of the Earth is what it is. The only input of energy that we have to the Earth is sunlight, and the sunlight arrives at the speed of light. And the Earth's surface loses heat via convection and evapotranspiration. That's the latent heat effect. And that's actually the process that we call weather. And these processes transport energy much more slowly than the speed of light. So the cooling of the Earth's surface continues after the light of the sun is gone. Weather is the chaotic process by which the Earth loses its excess heat without ever reaching equilibrium, and it's driven by convection. But then in the upper atmosphere, eventually, all the energy does have to leave via radiation. So because radiation is the only method to actually get the heat back into space. It's just, and I think the misunderstood concept here is that the radiation doesn't have to leave as pure radiation. Any excited molecules in the upper atmosphere, as they fall to a lower state, are going to emit radiation. And it's a very, very complex process. It's a very chaotic process. But so I'm not arguing that the energy doesn't eventually become radiation in the upper atmosphere. I'm just saying that in the lower atmosphere, radiation is a very, very minor player, if it's a player at all. And so how did science get this wrong? Well, the Stefan-Boltzmann law only holds strictly at zero Kelvin. And 0 Kelvin, people think of it as being very, very cold, but what it really is it's a perfect vacuum where there is no molecular activity of any kind. What I found is that this particular point is often ignored, and it's a very important point because if you have a black body in a vacuum, it will emit radiation at a certain rate based on its energy and the rate of spontaneous emission by atoms there. If you put it into an atmosphere, the collisions with the atoms in the atmosphere are going to remove energy by conduction, and that's going to perturb the energy balance at the surface of the black body so that the spontaneous emission by radiation will be greatly reduced. What's basically happening is that the conduction from the impinging molecules in the atmosphere are removing heat more efficiently than radiation would. And in fact, what will happen is the body will cool off much faster as soon as you introduce an atmosphere than it would if it was losing heat by radiation alone. And this is something I learned when I was working with vacuum processing for semiconductors. And in certain cases, you could have, in doing a process called molecular beam epitaxy, you could have a substrate that was heated to a point that it was orange hot, quite hot. And as long as you maintain the vacuum, even if you turned off the heat source that was maintaining its temperature, it would take a long time for that color to go away and to cool off. But as soon as you introduce a little bit of air, it cools off very, very quickly. And there are other cases, processing different types of components where we took advantage of this very property, that the gas would cool the component very quickly, but without the gas, it would stay hot for a long time. Anyway, so the second point is because of this 0K restriction, neither the surface of the Earth nor its atmosphere can be treated as black bodies. But that's what modern climate models do. In fact, there are a lot of online courses that talk about climate modeling, and they state very clearly in there that they treat the Earth as a black body, and that's where they get the 398 watts per square meter. And then they treat the atmosphere as a black body, and the atmosphere is a little bit cooler, and that's where they get the 340 watts per square meter. But at the Earth's surface, at atmospheric pressure, there are about 100,000 air molecules colliding with the surface for each potential photon that's emitted based on the Stefan-Boltzmann law. And the detailed numbers of that are in my paper. And that explains the much greater energy transfer by conduction and convection. We're looking at 5 orders of magnitude of molecular collisions versus potential photon emissions. And then I just have some closing thoughts. The concepts of the greenhouse effect and radiative forcing as applied to climate change only exist in models in the minds of those who believe them. They don't represent the real dynamics of heat transfer in an atmosphere, which is perfectly demonstrated by the operation of the Pirani gauge. The energy input from the sun drives climate and weather on the Earth, and the Earth climate and weather system responds via evapotranspiration, conduction, and convection according to the laws of physics. And this does not include an imagined recycling of infrared radiation in the atmosphere. And I'd like to say I give express permission to share this information freely. I think the more people who are willing to read this and potentially try to understand this, the better off we'll be. I think that the climate realist community needs to change its narrative a bit, and we need to shift from an argument regarding the degree of radiative forcing and greenhouse effect and how much, whether it's going to be really bad or not so bad, to actually just falsifying it as an invalid hypothesis, because quite frankly, the laws of physics don't support it. And then I just also mentioned, that this is all based on very old ideas. The concept of warming due to gases in the atmosphere was first proposed by Fourier in 1824, and by Tyndall in 1859, and then Arrhenius wrote a paper in the late 1890s. But none of those proposals gained any traction at that time, and you have to ask yourself why. And this is maybe more of a geopolitical and social comment, but it was only in the modern era, with the potential for massive government funding and the creation of a continuing crisis, that this concept entered the mainstream. I have looked far and wide on the internet, and I've never found anyone who has tried to fact check this concept. And that's why I'm here. And I think that's it.
I just wanted to say a couple of things before I ask you questions. One thing is that if you want a better look at the figures, I put a link to the slides in the show description, so you can go ahead and blow up the figures and get a really good look at the figures. And also, you mentioned your white paper. I also will have a link to that, so you can go ahead and read Tom's white paper. Then another thing is that just yesterday, What's Up With That put a post up about this very topic, and it already has 118 comments now. So if you want to go ahead and read what people are saying about it, you can go over to What's Up With That. And I'll put a link to that in the show notes too. Yeah, and my questions are, have you looked carefully into some of the other people like Marcus Ott, there's Kevin Kirchman, Howard Hayden, Yang Zhang? Do you think they are sort of on the right track? They're not measuring things, but they also share your belief that the greenhouse effect might be zero. Any comments on that?
Yeah, and in fact, I'm glad you asked me that question because I have watched all of your presentations with each of those gentlemen. I think Marcus has done maybe 4 or 5 of them so far. And what excited me about them is that there are other people here who disbelieve in this business as much as I do. And I think there are many paths to the answer. It's only been in the last year that I really became focused on trying to figure out how to fix this, because I've said for many years to people who bring up the topic of global warming with me, I would always say, it's a bunch of rubbish. There is no greenhouse effect, and sooner or later somebody's going to figure this out. The situation politically and socially has just become so bad in terms of what this global warming and carbon phobia has done to our society that I decided I needed to work to get there. And I had the maybe serendipitous benefit of having worked in the industry that I worked in, because ultimately, in order to disprove it, you have to have an experiment that disproves it. I think all of those gentlemen you mentioned are doing great work. And, if I hadn't been so focused on putting all this together, there were some of them I wanted to contact and share some of this with them. And I hope maybe that they're watching your podcast too and will see this. I think they're great thinkers. I think what's really important today is that we need people who can think outside this greenhouse theory box that our society is trying to put us in, and be skeptical about what the mainstream scientific community is trying to tell us. In fact, I think I remember Yang Zhang in particular mentioned that there needs to be some kind of, coalition of really serious skeptics who are dedicated to basically, I view it as kind of, putting a stake in the heart of this whole greenhouse theory business once and for all, because it's unphysical. And I know that I'm not the only person that feels that way. And I also hope that with this information showing that there is a way to experimentally show that radiation is not a driver in the atmosphere, that more people who understand this will be willing to speak up about it. Because there's also that pressure in our society now. You don't like being called a denier or any of the less complimentary things that the other side comes up with.
Okay, and maybe you already explained this, but how about additional water vapor in the atmosphere or additional clouds? What is the mechanism for how that might hold heat?
Well, I think, clouds and the whole issue of water vapor, evaporation, all that are very, very complex. I don't think it has anything to do with radiation. Water evaporates. I'm going to take just a very slight digression. Water vapor is very important in the dynamics of the atmosphere, not because it's a greenhouse gas, but because the more water vapor you have in the atmosphere, the more energy a fixed volume of air can hold, right? So, and I think one of the grave errors in this whole discussion is we shouldn't be talking about the average temperature of the Earth. I think a more important parameter would be what is the energy content of the atmosphere, because we could have a desert at 120 degrees versus with 3% humidity versus the tropics. I'm just kind of pulling numbers out here versus let's say versus a subtropical area at 70 degrees with 80% relative humidity. And I mean, I'm just saying these numbers off the top of my head, but clearly you can have a situation where the temperature is much cooler, but there's much more energy in the atmosphere. And water vapor, I think, does play a significant role in heat transfer. When water evaporates, it rises. It's carrying heat with it. When it gets into the upper atmosphere and it condenses and it cools and it condenses, it releases energy. And that energy, some of it is going to excite air molecules that then may release radiation. There may be some radiative component of the condensation process itself. I haven't looked into that. That was a question that just occurred to me the other day. But no, water vapor is extremely important. So I'm not trying to discount the role of water vapor at all. My whole point is to show that radiation is not a player in terms of radiative heat loss from the planet's surface through the lower atmosphere is not a major player in this argument.
What do you anticipate would be the biggest objection to people who actually read what you have to say? What do you think they're going to say, and how would you counter it in terms of objecting?
Well, I've read a few of my comments already. It's difficult in some cases because, clearly some people who object, they object simply on the basis that they think they're right and I'm wrong. But, I had one person object and they said the Pirani gauge isn't a good model because it's a small enclosure and this and that. And I didn't mention it in the presentation, but I do mention in my paper, you can have a naked Pirani gauge and you can take it up into the atmosphere 100,000 feet. And it's going to register the same pressure that it would register if it was in the enclosure. It's because what's happening that's critical isn't about what the volume is or what the enclosure is. What's critical is what's happening at that surface. In the case of the Pirani gauge, it's at the surface of the filament where there are, many orders of magnitude more air molecules hitting it than there are radiation photons leaving it. And likewise, at the Earth's surface, the example I gave is that there are 100,000 molecules striking the surface of the Earth, and the mean free path at atmospheric pressure is so short. It's about 70 nanometers, which is about 1/10 the wavelength of light. So this conductive heat transfer that happens at the surface of the Earth is happening over a very, very small distance, certainly less than a micron for the most part, because the air is very, very dense. Just a little factoid from my paper. So an average air molecule is moving faster than the speed of light. An average molecule collides with another air molecule about 7 billion times per second. This is all in my paper. And as you're sitting or standing in the environment of our atmosphere, the rate of collision of molecules with a surface is it's on the order of 10 to the 27th power collisions per second, which means that as you and I sit here, 10 to the 27th power collisions per square meter. So as you and I sit here, our overall body surface area is probably in the neighborhood of a square meter. And that means every second we're being pounded by about 100 pounds of air molecules. But we don't feel it because they're all so small and it all balances out. But each one of those is taking energy from our body because our bodies are generally going to be warmer than the surrounding atmosphere. And on a hot day, we sweat, and then the evaporation of our sweat takes energy away that way. Do we radiate? Yeah, we radiate a little bit. That's why, infrared cameras can see people in the dark and things like that. It's not that there's no radiation. It's just that it's not the primary energy transport mechanism to take heat from the surface of the Earth and send it back into space.
I was just looking up here, the cost of a Pirani gauge. It looks like it's like $350 on Amazon. Do you think there would ever be a time where you could get like a college physics department and have them get their own gauge and see this for themselves? Is there a lot of other expense other than having the gauge in order to replicate what you did?
Well, the odds are most college physics departments probably already have one somewhere. The Pirani gauge is an extremely common instrument. Virtually any system that semiconductors are processed in, or any kind of thin film devices are processed in, all of this is done in a vacuum environment. Even flat panel TV screens, reflective glass panels that go on buildings, things like that. Those are all thin film processes that occur in a vacuum. And so Pirani gauges are everywhere. I wouldn't be surprised if there were hundreds of thousands of them in operation. So any college physics department that had any kind of a vacuum system would likely have either a Pirani gauge. There's another gauge called the thermocouple gauge, which operates on a similar principle. It uses a thermocouple junction that has a constant current passing through it, and they monitor the temperature change of the junction as a function of pressure. The beauty of the Pirani gauge is that it gives us a direct power measurement of how much power is being removed by the gas versus radiation. But they both operate on a similar principle.
All right. I'm excited to get this up on YouTube and get the comments rolling there. Would you participate at all in comments if people have questions there, or on What's Up With That? Or
Oh, absolutely. Yeah. Yes, I plan to. Like I said, the What's Up With That happened. I didn't know it was going to go up quite when it did. I was a little unprepared, but I'll probably be working on that starting when we're done here.
Any other questions that I should be asking that I did not ask yet? Or any other points you'd like to make?
Well, just that I think that, and this is more a personal opinion than a technical point. I think we're living in a bit of madness now, where everyone is afraid of carbon, which is such a beneficial. It's a necessary part of our existence, and without CO2, we would not have a living planet. And I think we need to figure out how to get together and put it into the madness.
Thank you for taking the time here. I really appreciate it. And let's let the comments start rolling in.
All right. Thanks, Tom.
All right. Talk to you next time. Goodbye.
Bye-bye.